Welcome to these tutorials that I've prepared on using FreeCAD and analysis software linked to FreeCAD. There are 4 in total. I've listed them at the bottom here. First of all, and this tutorial, we'll be covering a development of a model using the CAD options within FreeCAD. I'll then be showing you how to mesh this model, apply loading boundary conditions, material properties, and do a mechanical analysis. The mechanical analysis will be first of all a linear stress analysis, and then I'll also show you how we can go a bit further and do a nonlinear elasto-plastic stress analysis. The other tutorials will cover thermal and thermomechanical analysis. I'll do an eigenvalue buckling and frequency analysis, and then finally I'd like to show a computational fluid dynamics analysis, which uses the open source CFD code OpenFOAM, which can also be linked to FreeCAD. These are different examples to the ones I did in the book. I think using these video format, we can show some different options. And in any case, I think it's interesting to try something different to what's in the book. So this first one, I should move on and just show you, it will be this mechanical analysis. So for this first example, I'll describe the problem and give a bit of background information. I'll then move on and show you how to create the CAD model. I should state at the very beginning here, I'm not an expert by any means on using CAD software, but I think what I can show you will give you a useful starting point. I'll demonstrate the meshing. We can experiment a bit with different meshing possibilities within FreeCAD. Then I'll define boundary conditions, loads, and materials, and then we move on to the analysis. As I mentioned, first of all, we'll have a linear stress analysis using CalculiX, and then visualization of these results. And then I'll move on to an elasto-plastic stress analysis. So this becomes then a nonlinear problem. Just to give some background to this, you can see at the top there a so-called notch specimen. This tends to be used for calibrating failure models, metal failure models. These are just the loading, just for the loading mechanisms in the testing machine. So ignore this and at this end. And what we've got in this case are 2 notches shown here. And the idea of this particular specimen is that you'd essentially have a mode 1 normal stress created here and failure. This would be one coupon. And I think you could imagine you can have other coupons with notches that would be offset. And such notches would create a combination of normal and shear stress failure. And this is another notch, just a CAD drawing of a notch, where we have, in effect, pure shear being created along this line here. So if you had a set of these notches with different loading mechanisms taking place at failure, then you could use these to calibrate a failure model for any kind of loading. Now CalculiX doesn't have these sort of sophisticated models, but I'm going to use one of these in order to demonstrate creation of a model and an elasto-plastic stress analysis. I've selected the one at the bottom here because it allows some possibilities to show some interesting things in the CAD modeling part of the exercise. The notches are inclined like this simply as a way of getting better load introduction into this region. In this tutorial, I would like to show the connections between the theory we've been covering in the different videos on the different chapters in the book and the options we will be using within the code. First of all, just to mention something on the units we're using. FreeCAD does have a range of different units that we could define. There is a default set of units. I'll show you that when we come to using FreeCAD. But irrelevant which set of units you define, the data will be written out in this set of units. And this is the set of units that CalculiX uses for analysis. This is a consistent set of units, and I discussed the issue of consistent units in lecture number 7. So the video on lecture number 7. It's very important in any finite element analysis that you use a set of units that is consistent. CalculiX would accept other units. There's no reason to stick to any particular one, but it is important that the set of units you use is consistent. And in this particular case, FreeCAD always writes out in this units. It's a 2D problem we're going to analyze. I'm going to treat this as 2D, but CalculiX or FreeCAD will write out the model using shell elements of type S6. Now, I did mention these elements in lecture number 2. It is strictly speaking a 3-dimensional element, but you can analyze 2D problems with the element. It is important to appreciate that it's a 3-dimensional element because it does mean you have to define some boundary conditions to make sure you don't have rigid body motions in the outer plane direction in the third direction. I'll mention this when we come to it in defining these boundary conditions. The elements used are triangular elements. They use a simplex formulation, and that's been described in lecture number 2. For the linear analysis, we use a simple elastic isotropic material law. I covered those in lecture number 6. And for the nonlinear analysis, we use a plasticity model, isotropic plasticity, and I covered that in lecture number 6. The data we will add for this plasticity has to be added in the input file. We can't do this in the FreeCAD software at the moment. It has this curve that I'm showing there, defined by a number of points, by 3 points shown here. So that's this point, and this point. And each point is defined by the yield stress, or the stress, and the plastic strain. Plastic strain occurs from this point onwards, and this is the elastic strain. You get this elastic strain from the modulus of the material, 210 gigapascals, and the yield stress. So you can see here the plastic strain values. These are temperatures. It is possible with CalculiX to have temperature dependency if you were trying to link a thermal analysis with a mechanical analysis. We're not trying to do that here with this example, so I just used the same temperature here, but if you did have a temperature analysis, temperature dependent properties, you could repeat all of this down here with a different temperature for different properties, and the code would then interpolate for any given temperature. And finally, just to mention, for this last elasto-plastic analysis, a Newton-Raphson solution is used, iterative solution. I did cover this in lecture 3, although in that lecture I discussed it in the context of large strain, large displacement analysis. Here, this particular problem is a small displacement problem. The nonlinearity comes from the elasticity or the elasto-plastic matrix for the material as it plastifies, and the stresses are no longer linear related to the strains, and we have an iterative solution necessary to find the stress state that stays on the von Mises yield curve for any given displacements or strains. So that's a bit of a brief overview, trying to link the exercise we'll be doing with the theory in the book. I probably will mention some of these points again as we go through them in the next part, which is creating the CAD model and doing the analysis. So I've now started FreeCAD. I should say at the start, this is version 19.3. It's running on Windows. If you want to download this, it's very easy to do. Just look under Google for FreeCAD downloads and you'll come to it, or I explain or give the links in the video on lecture 7, concerning lecture 7. The first thing I'd like to explain, I think, is the some of the viewing options. If we go under Edit, Preferences, you will find certain so-called workbenches shown here, and viewing options. And for each of these, we can change certain information like the background colors or line thicknesses and so on. And once we activate other workbenches, which I will be showing, then more items appear down here. First of all, under General, we can look under Units. And down here, we can see a whole set of unit systems that FreeCAD will allow us to define. I always use the standard at the top there, so this would be the default. Everything will be specified, or results viewed, in millimeters, kilograms, seconds and degrees. But as I mentioned earlier, this is not a consistent set of units, and the output to the file that will be run by CalculiX actually uses this set of units. Now you could specify this, but I don't find some of the information stored particularly in the materials database very convenient in this set of units, so I don't tend to do that. I leave it on the standard. This allows you to change, for example, the number of decimal places. Again, for the various properties, I leave the default there. There's nothing else really I want to show there at the moment, so we just say OK. The other thing to make sure is that under View, Panels, you have the Tree View and at least the Combo View active. It can also be important or useful to show the Report View. That would be another panel at the bottom which shows possible error messages. I'm not going to activate it here because I want to keep the screen as large as possible. So we'll leave that as defined there. Okay, first of all, we'll go through this panel up here. Opens all of the workbenches, so-called workbenches. Now I only know a few of these. In all the time I've been using the code, I've only needed to use a few of these. But for example, we'll start off by going through to the Sketcher workbench. And the first thing we have to do is here with this panel, this icon right on the left, we have to activate a certain viewing plane. I'm going to use the XY plane here to build this particular coupon model. So I say OK. And now we can start creating the coupon I showed a couple of slides back, which was this rectangular coupon with the two oblique or inclined notches. Now up here we have two sets of commands. These allow us to define certain shapes. And then these commands here, plus a few more defined here, allow us to define constraints. Perhaps the best is I'll just show, for example, the rectangle. I'm going to draw a rectangle to represent the outer shape of this coupon. Now I could try to do this accurately with the cursor, and you can see coordinates there in the bottom right in blue, 115.5 for X and minus 27.6 for Y. I could do this to try and create the 100 by 20 millimeters dimensions for this coupon, but that's not really the best way to do it. The best is to just simply drag a shape. You click again on the right hand, or with the left mouse key, you click again to sort of close the option, to complete the option. And then with the right mouse key, it will stop these operations. So we've created one rectangle. Now this has certain constraints which are listed down here. There's a total of 8 constraints. The first 4 are saying basically that this line, which has a point here, and this line, which has a point here, these 2 points are tied together. That's our constraint 1. Exactly the same applies for the 2 points which are constrained together here. And we've also got this here and this here. If you highlight one of these, you will see it turn green. So actually this constraint 1 is representing this point over here. And 2 is this point. The other 4 constraints are for a horizontal line. So it's saying that this line has to be horizontal and this line has to be horizontal. Similarly, we've got 2 vertical line constraints here and here. Now those set of constraints really means all I can do, if I click on here, I can move this line this way, and I can move this line here in this direction. But no other movements are possible with this set of constraints. Now we can dimension this part. So for example, using this option, for a horizontal distance between 2 points, I click on that. Sorry, I have to click the 2 points first. I'll do this, and then click here. Let me start again. This point and this point, clicking here, I can now specify 100 millimeters. Notice that FreeCAD gives you the units to be used. If I'd selected a different unit system at the very beginning, I would be seeing different units here perhaps. But in this case it's 100 millimeters, okay. That will set my length. I only have to do it for one of these 2 lines. The constraints force that this will also be 100 millimeters. And now I do this point and this point with a vertical constraint of 20 millimeters. So this gives me my coupon size. I'd like to center it, makes life a little bit easy. So I'm going to use this point and this point with a horizontal line and put 50 in here. And I'm going to do this point and one of these points, this one will be fine. And I'm going to put in 10. So the whole thing now is fully constrained in the center. I cannot move this in any way now. So next we want to create the 2 notches. I'm going to use this slot option here. Now this can either be vertically like this, or it can be horizontal like this. Because of the constraints that will be created when doing this option, it can only be horizontal or vertical. We click again to finish the size. So I've just positioned this in any position and any size at the moment. I use the right mouse key to stop that, otherwise I would end up creating another one. Now you can see we've got a vertical line constraint created here and here for these, and we've got a circle, and these constraints, so this one here and this one, force that this line and this half circle have a tangent. at this point. It is in effect this one here. Okay, now if I want to rotate this, I've got to delete this vertical line constraint. I click on it, and then with the delete key, it's gone. I'm now in a position to rotate this round. So this starts to look like the notch we want. I'll now try to position it. So what I'll do is I'll click on this node and this node and use this with 10 millimeters to set, sorry, I wanted to have 5 millimeters there. Double click on it again and correct that. So this notch will be 5 millimeters away, and the notch I'm going to place in here will also be 5 millimeters. Then I set a vertical constraint between this point and this point using this, and I'm going to set it to be 2.5. Did that wrong. Yeah, so that's position this point at the right position, but what's wrong at the moment is that the dimensions of this arc are not set to 5 millimeters. We can do this by clicking on here and using this length option. And if I set this to 5 millimeters, then we see we've got the first notch at least having the right dimensions and in the right position here. Now the next thing, we want to set it to be an angle of 45 degrees. We can do that using this constraint here between this line and this line. It's done the reverse of what I wanted, but if we set there 145, sorry, I'm making a lot of mistakes here. That should be, of course, 135. I can correct that. Perhaps we should also check that that line and that line are also at 45. Okay. Well, in fact, this is just setting one of these lines has been sufficient because of all these other constraints in this geometry. It has to be 45 anyway. We can now clean this up a bit. We use this trimming operation to delete this, this, and this. The last part, a right mouse key to stop those operations, then we click over this, drag a box over it, and the delete key, we can get rid of that. So we've created our first notch. I'm now going to create the second one. Of course, you could do it in exactly the same way, but I'll try and use some other operations just to show you some other features here. We can clean this up a little bit. It looks a bit of a mess. You just simply go on to the one you want and drag these away. There's another one there, but it doesn't matter. Okay, I'll zoom in a little bit. I've done that by the scroll on the mouse. Now what I'll try and do, I'll specify a line in here. Click on it, and then we'll do another line. And the right mouse key to stop these. I'll do a circle, or at least an arc. I use this operation here. You do the center, come out to the first point, click, and then you drag out your arc. And the right mouse key to stop that. Now, this one is connected already. This one was not close enough to cause a connection there. So we use this operation here between this node and this node to connect those. And the right mouse key to stop that. I then use this tangent icon here to force that this and this are tangents, and also that this and this are tangents. I'll zoom out. We could use this operation to force that this line and this line are parallel to each other. And I can use this well, I have to specify a size, of course, now for this whole thing. Let me try that with this operation. And we'll specify 5 millimeters. I now use this one between here and here, using 5 millimeters, and then between here and here, and this icon with 2.5. So we have it in the right position. Now we have to have the angle correct for this. So I come again in here, activate this constraint between here and here, specifying 45 degrees. Okay. And so we have it now constrained in the right position. And then finally, of course, I've got to use this operation to clean these. And that's our geometry. There are lots of other things I could show here. For example, this would be a fillet operation. If you then specified these two lines, it would create a fillet. We don't want that, so very conveniently here we have an undo button to get rid of the command I've just done. If you wanted a circle, you'd use this one at some position, and then you'd specify the diameter or the radius using this operation. So I hope that gives you some kind of a introduction to how CAD geometry is created. We now will finish this. That is done using the icon here. And here we can see our geometry. That basically completes this sketching operation. We move through up here to the part. And what I could do now, if I wanted to do this as a 3D geometry, I could click on this and use the extrude option. There is a dimension for how much I wanted here. It's set by default to 10 millimeters. If I do apply, I will then get a 3D geometry. But if you remember, I said at the beginning, I'm going to do this as a 2D problem. So we're not going to do that. I'll use the undo button to go back. We have to convert this to a face. So we click on this, and under this part, make face from wires. I click on that, and I've created now a face that we can go about meshing. We now move through to the next workbench, which is FEM. Here in this work package, or workbench, we can now start creating a mesh, creating loading, boundary conditions, materials, and do the analysis. I'll start off by clicking on this and using the G-mesh mesher. So that's up here. We'll define a maximum element size. Let me put in 3 millimeters. Apply. And this is typical for the G-mesh mesher. You get a fairly regular mesh. There are some tools to try and refine the mesh in certain locations. For example, we would like a finer mesh around here and here for this region. I will show it, but I know that in this Windows version 19.3 it doesn't seem to be working, or perhaps I make a mistake. So let me say OK, and I'll click on that. Sorry, I activate. You click on this and you say show selection. These panels here open, or these icons open. Now under this one, it should be possible to, let me close this window, at this report window at the bottom, because it's losing space for me. Sorry, under Windows, Panels, Report window, we'll close that. If I add this, I add this edge to these lists here, and I specify, for example, 1 millimeter, it should be possible to have a locally refined mesh there. We say OK, and then we'll repeat the meshing operation. And as you can see, it's really not working at all properly. I have used this operation before in version 18, and it did work for me then. So there does seem to be some problem there, or maybe I'm making a mistake. So I'm going to cancel this, and we're going to delete this mesh here, this G mesh. You just click on it. You can see here the boundary that we created. We delete that, click on it, say delete. And you click on that as well. With the right mouse key, you say delete. So we've got rid of that. I'm going to use the NetGen mesher and do this. The best way to proceed, I should really have started an analysis container. So that comes here. And everything we have now for the mesh, the loads, the boundary conditions will be below this analysis container. So that's created using this symbol here. This is our tool for running the code. We will use that in a few minutes. We'll create a mesh. So I click on here. I use the NetGen editor. I'll use a element size. Let's try again with 3 millimeters. No, let me just show you an example. Let's take a very fine mesh and do apply with all the defaults. It's not a bad mesh, but it's obviously not fine enough in this region. So I'm going to use the user defined. I'm going to specify maybe 3 millimeters. I can, with these options, say how many elements or how many segments are along here, and how many elements or segments are around the radius. Now this option, as far as I can understand, says how many elements you have in every one radian. If I put in for maybe 5 here, these are our radiuses, we should see a much finer mesh here. We'll say apply, and that's not bad. It's not quite what we want. The grading between this and this region is not particularly good. So I'm going to use a growth rate of 0.1. Now this is saying basically the element sizes, how much they can increase as you move from one region to the next region. Obviously with a smaller number here, we're going to have a better grading. We'll try apply again. And that's really not bad at all. If we look closely, the elements are really quite good. We have some windows up here to give better viewing. So for example, this should be the top view. With the scroll on the mouse, I can go in and out. You can, with the shift and the control keys and the mouse, you can do rotations and translations. So for example, this will allow rotation. That I'm using now the shift key and the right mouse key. Here I'm using the control and the right mouse key. Best is just to practice with those yourself to see how they work. I think we'll use this mesh. It's not perfect. Perhaps we'll use a... No, it's okay. We'll use this mesh. Okay, so we've got our mesh. We'll do an analysis. First of all, we have to define some constraints. So I'm going to click on this icon here. Add. Click on that and say add. It's a little bit confusing with FreeCAD. Sometimes you add and then click on the item, and sometimes you have to click on the item and then say add. So this is our edge. We're going to fully constrain, and in here you just put fixed, fixed, and fixed. Now it's a 2D problem, but as I mentioned, we're using shell elements, so it does have a degree of freedom in the out of plane Z direction. So something should be fixed to stop rigid body motions there, and so I fixed it here. So this is all fully constrained. Rotations for a shell element usually have a lot of sense, and you have to constrain those as well. But this is using a pseudo shell element, which is I described it in the book. It's a solid element that's extended, and it behaves rather like a shell element. It doesn't really matter about constraining the rotations, but I'm going to do it anyway. Okay, so we've fully fixed that. We're now at the other end here. We're going to apply a displacement. So we'll take this. We'll, again, same mistake. You click on this, add. And down here, I'm going to say it's got an X displacement of 1 millimeter. And the rest of the directions I'm going to fix. Okay. In this one, I fixed everything using these operations. I could have done it slightly different. Let me delete that. So you click on it and say delete. You can use this operation here to do the same as what I just showed you. You click on there, add, okay, and that means this end is fully constrained. Those two methods would give you exactly the same behavior. So we've got our loading, we've got our constraint. We need to define a sheet thickness. We do that using this operation here, this icon here. Shell thickness. I'm going to put, well, Let's put 1 millimeter. Add. Okay, one moment, I have to make this visible. Click on that and say show selection. I'm not sure why that's not being added. It's not actually important because it will take that anyway. If you have several parts in a model, each with different thicknesses, then you would have to add these individually and give each one a separate thickness. But we don't actually need to, since we've only got this single part within this analysis. So we'll leave that at the moment. If I go to this panel, this icon here, I can define the material. Click on that, and we see now the database that's available in FreeCAD. If I come on here, I can go down. I'm going to use CalculiX steel. So this just defines standard steel properties, but there's a whole range of materials here. This is a typical aluminium. And here we have standard steel. So for example, it defines density. It's not important for this analysis. And the thermal properties are also not important. But this is the modulus, 210 gigapascals, and this is the Poisson's ratio, and we do need this information. So we'll say, okay, again, we don't have to add the material in here. Again, we'll have the same problem. There's something a little bit strange there. I don't know why it's being added, but we don't need to do that at the moment. So we'll say okay. And that's basically everything we need defined, and we can do an analysis. We double click on this solver. Now in here, you can either have a temporary working directory where results are stored, or you can specify a directory where you want to store the results. I will use a location. I come in there. This one is a directory I previously set up. Select folder, and then we write the input file and run the analysis. We could have write the input file and then edit it and then run the analysis. But in this case, I didn't want to make any changes to the input file. I don't need to see it. So it's done the analysis. I can say close now. It's replied done without error, close. And down here, I will have my results file. That's this one here. I can double click on that. And for example, if we say displacement magnitude, we have a contour plot of displacements. There's no legend here, but I can show you how to get that in a moment. But we see that the minimum is 0. Okay, that's the end that's fully constrained. And the maximum is 1 millimeter, which is correct. We've applied a 1 millimeter displacement. I'll close that. We can also do maximum principal stress or von Mises stress. Von Mises stress is not only for a elasto-plastic analysis. This is just a quantity of stresses. I did go through it in lecture 6. We can plot that if we wanted to, and you can start to see in here and here high stress concentrations. The same if we look at maximum principal stresses, you can see the values in here. This gives you slightly better plots, this pipeline option. If we click on that we don't get anything much at first, but then this new results has been generated. Double clicking on here opens this panel, and if we say maybe surface, and then we select perhaps major principal stress, we see now a legend here and the stress concentrations. We can get rid of this, move it away. You click on it and just drag it across to some other position. It's something to allow you to move around. So we have a maximum stress for this 1 millimeter displacement, which is extremely high. It's 13. We're in the units of gigapascals here. 13,000 megapascals, 13 gigapascals. So this is extremely high. I'm going to do an elasto-plastic analysis next, and I know that this is way over the yield stress of the material. We would not get a solution. I will have to reduce the applied loading from 1 millimeter here to about 1.1 millimeter to do this sensibly. So I'm going to stop this now. But if you wanted to, you could look at other things here. For example, displacement magnitude, and we see correctly we've got 0 here and 1 millimeter up here. There is one other thing, sorry, I wanted to show. If you open this panel again, there is down here there is a nice option to magnify displacements. So if you drag this, you can see the displacements. Now these are not the real physical displacements, they are magnified by some value here. This can be useful just as a way of looking if the loading and the general displacements are what you expect. Probably I should put in a number, let's say 5 in there. And now you should have much more sensible magnification of the actual displacements. Okay, we'll close this. I'm going to do a next analysis. We're going to delete these results using this icon. We also delete these by clicking on them and then using delete. I'm going to change the displacement because as I mentioned, it would be much too much for an elasto-plastic analysis. So I double click on this, and down here I can put in 0.1 millimeter for the applied displacement now. We say OK. And I'm going to start the analysis again. Nothing else needs to change. We start the analysis, static, write input file. But before I run it, I edit the input file. We keep the static active, edit input file. Now this is our data set that's written out. It has the same structure as a Abacus file. There is an option which is activated in the preferences which allows you to split the file. So it's done that, and what would normally come here, for example, would be all the nodes, but all the nodes have been written out to this particular file, or this particular file, and it's included at runtime. It would be read in and positioned here. Similarly, this will be the elements or constraints. This is the elements, constraints, and so on. So we've just got a summary of the information that we're really interested in here. This is the material information, the shell thickness, 1mm. Type of analysis is done down here. Now we want to convert this to be elasto-plastic. For that, I have to go through to a file I have prepared. And this is the information. If you remember right at the beginning, I explained this information. It's to define the elastic plastic curve. We come back through to here, and just in here I paste in this information for the plasticity part of this material. So this is new. The fact that this plastic curve applies, or this plastic keyword occurs here, it means it will be a nonlinear analysis now. And these are my yield stress and strain and temperature values for this material. That is the only change I make. If, for example, I wanted to do a geometric nonlinear analysis, this is not a suitable problem, then in here I could have, I think it's NLGEOM, might not be 100% right, but you could type that in, for example, and then that would be a geometric nonlinear analysis. So there are things you can enter in here. These are things that FreeCAD is not able to create or output, but we can do it at this stage. CalculiX does understand them. It will do the analysis, and FreeCAD will be able to analyze the results from that analysis. So that's done. We say stop, or we're going to store it. We store the changes, and then we do the analysis. Now this is a nonlinear analysis. It may take a little bit more time, so I'm just going to stop the recording. So actually it didn't take so much time. We have here 18 seconds. I'm going to close this now. And down here we can see now we've got new results. This is a little bit confusing perhaps. You see that the thing here, time 1 and time 0. That means 0.88, time 0.5. This is something that all of these codes tend to do. It's not a dynamic transient analysis where time is really involved. It just uses time as a means of saying how far we are moving through the analysis. So time 0 means a start and time 1 means an end, but it's not a physical time of 1 second. I'm going to open this and we can see, for example, maximum von Mises stresses now. We'll look at a contour plot in a moment, but you can see the results are very different to before. We've got a fully, this should be a fully plastic region now existing in the model. We can see the minimum. There's some small amounts somewhere. Well, these small amounts were probably in this region here, I suspect. But we've got a maximum of 416. So the yield stress was 400, and we've got things around 416. So there's definitely plasticity here. I'll close that, and we'll have a look at that using this viewing option. This new icon here opened. We'll do surface. I'll come down and do von Mises. And indeed you can see we've got everything in this region. It doesn't look so good to me, but this region is plastified. Sorry, I've got it now. This region is above the 400. So we have a plastic zone developed. I think that's all I wanted to go through. I hope that gives you some idea how we set up a problem with the CAD, the meshing, the analysis for a linear problem. You don't have to make any changes to the data set, it will run. If you want to do a nonlinear analysis, then you have to go into the editor, edit in some information like this plasticity curve, and then the analysis will work. So as I say, I hope that gives you a reasonable introduction. The next tutorial I'll move on and I will do something on thermal analysis.